introduction. So it works so well with Docker. So raise your hand if you've used a knitting machine before. Oh, wow, a couple more people than I thought. But the good news is that many of you are wearing a knitted object on your feet, probably socks. So we're all machine knitting users by heart. So this talk is about machine knitting, which isn't really a common ICFP discussion. But on screen right here is this diagram of a knitting machine. And it's this fully automatic mechanical marvel, and it's roughly the size and weight of a fridge lying on its side. Super expensive too. They can be used to create garments of all shapes and sizes. And then if you take away one thing from this talk, I want it to be that machine knitting is this exciting and interesting form of non-traditional computing. And as PL researchers, we're used to improving computing using our research, so why not try machine knitting out? So to start out, I'll just have the basics of machine knitting. Every knit object is made up of these things called stitches. Every stitch is when I take a loop and I pull yarn through it to form a new one. So right here we've got 5 stitches out. With hundreds or thousands of these stitches, we can tile them together to form these functional and fashionable knitted structures. Knitting machines can manipulate yarns to do all this automatically with absolutely no help from humans required. And then they have hundreds of these hooks that will hold, pull, and transfer yarns to get the desired result that a programmer wants. So machine knitting is used to make almost all those knitted objects that you find in stores, including but not limited to socks, sweaters, gloves, and headwear. And then high-end knitting machines, the ones that we're studying in this talk, are quite powerful. They can make these beautiful patterns and textures and colors. And then they can also be used by researchers to make, for example, the graphics people have the Stanford Bunny. And then the soft robotics community has been able to use machine knitting to create some really cool tools there. So many machine knitting programs are written in these low-level languages that require the user to manually specify which actions the machine should take. And they're quite similar to assembly in traditional computing, but these languages are specifically straight-line execution. So there's no recursion, loops, or jumps. So these instructions are these atomic machine operations. For example, here's one operation that's performing a single stitch with one of those hooks. So it pulls the loop through the loop, and it creates the new one. Because these languages are so fine-grained, they're not easy to use. So programs can have thousands of these stitches, and managing this whole machine state can be very challenging on the programmer. I want to draw this analogy between machine knitting and traditional computing. So traditional computer operations are moving bits between registers, and machine knitting moves yarns between the hooks. So basically, the yarns are sort of the values of machine knitting. Traditional computing is often studied where the only observable behavior is the final state of the machine, what the result of the computation is. But in machine knitting, the observable behavior is this physical program trace. As the yarns move throughout the machine, they leave behind this literal physical 3D trace of the yarn. And so when you get the object out, that's really just a program trace. So this is my exciting takeaway. Your socks are physical program traces. So now back to programming these knitting machines. Researchers have developed these higher level languages and tools that can abstract away some of the details of the machines. And these high level languages will then compile down to those low level machine operations. They're generally much easier to work with. But there's this problem. Low level languages lack these usable, rigorously defined semantics. So as a design is compiled into those low level operations, there's no notion of program meaning to consult. And then because these equivalences aren't well understood, the compilers are quite conservative in their optimizations that they can make. Additionally, they can contain bugs, and then the high-level design tools often purposefully limit the expressivity of the garments they can create just because of the difficulty of effective program analysis to compile down to operations correctly. And then this is the problem we're addressing in this talk. We need to have semantics. This hopefully shouldn't be an unpopular opinion at ICFP. So prior work has developed a definition for machine knitting semantics, but those semantics are purely topological. So the programs would denote these tangles of yarn that are embedded in 3D space. Two programs are equivalent whenever
their tangles can continuously deform into one another, just like in knot theory. So topological equivalence does allow all sorts of stretching and deformations of yarns, but in the real world, there are some physical limits to how much yarn can stretch before it breaks. The two knitted objects actually have to have similar yarn lengths as well as the same topologies in order to look and feel the same. So this prior work and our work by proxy don't consider the yarn lengths, so that's a slight limitation, but we do believe that those yarn lengths could be added in. We're just focused on the topology for now. So an important technicality is these authors' uses of these dashed lines right here. They exist to topologically separate the stitches from the other parts of the work. So they prevent the yarn inside the dashed lines from escaping and interacting outside. So you can think of it as if I've nailed down the yarns at each of those points along the dashed lines. So because these semantics are relying on continuous deformations, they can sort of be unwieldy. The authors only described a limited set of program rewrites in their paper, but in our semantics, we're able to fully characterize program equality. Now, we're deciding machine knitting program equivalence in polynomial time, which should be an alarm bell. Most languages don't have easy program equivalence, but remember, our language is straight line, so we have some hope. Knot theorists haven't been able to find an algorithm for polynomial time knot equivalence, despite working very hard on the problem, so many of them suspect that an algorithm doesn't exist. So instead of solving a long open problem in mathematics, we've noted that only certain types of topologies can be output by these knitting machines. And so we're providing a polynomial time equivalence procedure only for those knots that the knitting machines can make. So we're encoding our topology using category theory. So to summarize, machine knitting is a pretty important fabrication technique, and there are a lot of connections to programming languages, but there aren't computable semantics yet. So now I want to discuss how we've approached this problem. So our work has adapted those previous topological semantics, and we're instead using string diagrams to discretely characterize the knitting topology and almost all of its equivalences. And I see some laughs there. Yes, the string diagrams are actually string diagrams now. So due to some quirks in how yarns begin in the knitting machine, our semantics don't capture a limited class of equivalences at the very beginning of some programs. We do have some future plans to adapt our semantics to recognize these equivalences, but the vast majority of the equivalences are captured by our models. So our diagrams represent the topology of yarn in 3D space. So whenever two yarns cross, one goes above and in front of the other, and that matters. So these two diagrams on the left are different. For those of you who are familiar, it's a braided monoidal category. And then our diagrams are actually graphical representations of a morphism in a category that we define in our paper. We'll use the diagrams wherever possible in our presentation, but fear not, category theorists, there's plenty of notation in our paper. Now, our semantics don't represent all knots. Knitting machines don't allow yarns to turn around and change direction outside of the stitches. So this restriction is what's allowing our program equivalence to run in polynomial time as opposed to general knot equivalence. So our semantics are suitable to serve as an intermediate representation for machine knitting. So a high-level design tool could target our semantics, and then a single compiler could translate to these optimized and correct low-level machine instructions. We also have some hope that our semantics might enable functional and formal high-level machine knitting tools. Our second contribution is a canonical form for our categorical semantics that we can compute in polynomial time with respect to the program length. This was surprising given the difficulty of knot equivalence. So this gives us polynomial time program equivalence because just given two programs, we calculate their semantics, calculate their canonicalization, and compare directly. Because our semantics are representing the topology of knitted objects, our canonicalization can be interpreted as this deformation of yarns in 3D space. So our equivalence algorithm has some immediate applications in translation validation, but the theory that we developed has some broader applications in the formal study for machine knitting. And this is the key contribution of our work. We are canonicalizing programs in polynomial time by deforming their output objects in 3D space. So our semantics are based off of this correspondence between certain monoidal categories and the topologies of string diagrams. So category theorists have formally proved that the topologies of these graphical diagrams are faithfully representing the monoidal categories that they're meant to. And we're using their result in reverse. We're instead representing our topology with category theory. So we represent machine-knitted objects with the axioms of something called twisted involutive monoidal categories. These add some more 3D structure to braided monoidal categories. The objects of our monoidal category are these lists of yarns where the list forms the monoidal structure. The identity morphism just keeps the yarn straight and unchanged. Stitches are represented by morphisms as they map one list of yarns to the other. And it's not critical for our presentation here, but our diagrams are read bottom to top because that's actually how knitting machines create the objects. We draw the monoidal product as a horizontal concatenation. So given any two diagrams that represent morphisms, their monoidal product is just those two diagrams next to each other. They're being knit in parallel. And then there's this braiding isomorphism that crosses one yarn over another, and then its inverse is just the opposite crossing. And then here it is in the context of a monoidal product. And then finally, we can draw a categorical composition as vertical concatenation. So given any two diagrams whose yarn objects agree at the boundary, we can just compose them by pasting them together vertically. We're knitting them in sequence now. So the big takeaway of all this is that each of our string diagrams are actually morphisms in a monoidal category. And every portion of our diagram is a morphism of our category, and these morphisms will tile to form the knitted objects. Now, in most diagrammatic contexts, equivalences like De Morgan's law right here can change a diagram's connectivity. So here, 3 gates are equivalent to 2 gates. But those prior semantics or machine knitting stated that those internal yarns cannot interact with the outside because of those dashed lines. So for the purposes of equivalence checking, we can temporarily just ignore those internals and draw all of our stitches just as these boxes. Categorically speaking, the algebraic structures representing these stitches are free. There is no way to rewrite compositions of stitches. It just is what it is. This is a key insight because now we've reduced our equivalence problem from the topologies of yarns to these comparatively simple string diagrams. Because of this, any equivalences between the diagrams come only from those axioms of twisted involutive monoidal categories. We formulated these 7 complete rewrite rules from those axioms, so diagrams are equivalent if and only if there exists some rewrite sequence between them. And then all of these rules have a physical interpretation, shown here. By setting up these semantics, we've reduced our problem of program equivalence to deciding whether there's a sequence of 7 rewrites between the diagrams. So to cap up so far, we've taken program equivalence to topological deformations, to category theory, and now into these 7 rewrite rules. And on our paper, we're defining this procedure that will canonicalize the diagrams up to those 7 rewrite rules. And I'd like to dive in on this technical point in our canonicalization algorithm. So our algorithm works in 3 stages, which use our rewrites in different ways. Our first stage is called layer. It pushes the complexity of yarn crossings down the diagram as much as possible. It operates as a top-down sweep. It simplifies the top of the diagram and keeps on pushing down and down and down before simplifying the bottom. After layer, we use swap to vertically reorder stitches to achieve a canonical order of them. So in this example, we just swap those stitches places. And then finally, we use braid to simplify any remaining yarn crossings. The most difficult part of our algorithm is the swap step because we somehow need to decide whether 2 adjacent stitches are able to swap places vertically. So this swap detection problem is really difficult because the diagrams are in 3D. On the left here, the stitches A and B can swap. A's red yarns both pass under B's, so they can just slide right past each other. But on the right, C and D are locked together. Due to those yarn crossings, those stitches are snagged on each other. And now I didn't run out of animation budget here. I just wanted to show this is a real world problem. This snagging problem is not an arcane categorical or topological construct. It is very much the same idea pictured here. The cables just are snagged. I cannot pull them apart. I cannot push them apart. So unfortunately, the snagging problem can be quite intricate. In this example, these two stitches appeared maybe to be snagged, but we later showed that they can swap. And then here's where our categorical representation will come in and save the day. We can use category theoretic techniques to provably detect snagging. So we'll use this simple example to demonstrate our snag test. We're interested in this middle chunk of yarns called X, and then whether it contains any crossings that will end up making A and B not be able to cross places. So objects like X are quite well studied. X is called a braid within the braid group, whose presentation is on screen. In fact, these three rewrite rules of our diagrams are exactly the braid group's presentation. And we'd like to separate X algebraically into two braids, which we'll call X sub B and X prime. The X sub B part should represent the portion of X that the B stitch can topologically slide past. And the X prime part would be the portion of X that it can't. That is, X prime is snagged with respect to B. I can't get rid of it yet. To achieve this decomposition, we can use a pair of adjoint functors. So our first functor rho will project out certain yarns in X. See our paper for the details. Here, rho is projecting out 2 yarns, leaving a strand on 4 yarns. And then we use a second functor phi to restore those yarns that rho projected out, constructing X sub B, the portion of X that can slide past the B stitch. After finding X sub B, we can just calculate X prime by subtracting out. And as we noted earlier, there's this adjoint relationship, and we in fact proved that they're a reflection, which means that repeated projections and reconstructions have absolutely no effect. The key idea here is that our braid functor composition keeps the X sub B part and destroys the X prime part. So after decomposing X, we can just slide the B stitch up past the X B, leaving only X prime between the stitches. And then because B can't slide past anything at X prime, A and B can only swap if A can slide all the way down past X prime. In our example, we've chosen X to have this straightforward graphical decomposition into X sub B and X prime, but it's certainly not common in general to have that. Now we're just going to repeat our trick, but for A, we're going to separate X prime into 2 braids, and then after sliding, we're left with X snag between A and B. By the previous steps, we can be certain that both A and B cannot move past X snag. So because X snag is not the identity braid in our case, we can safely conclude that A and B cannot swap places. And then in the converse case, A and B can swap places. Now, I said earlier that I'd show that this example is not snagged. Our first step will move roughly half of the yarn crossings below the bottom stitch, moving B all the way up past. But now there's really no clear relation between those because there wasn't a clear graphical decomposition. Our functors are doing all the heavy lifting here. Then our second step will just move the remaining crossings above the top stitch, showing that the 2 can in fact swap. But this isn't particularly satisfying, and I would forgive you if you don't trust me here. So I have one more animation to show you. So here's the decomposition of X into X sub B and X sub A that our functors calculated. There's this clear correspondence between X sub B and the braid that ended up below B, and then the similar for X sub A and the braid that ended up above A. And for our decomposition to be correct, we need some sort of rewrite sequence between our original braid X and those decomposed braids X sub B and X sub A. And then here's the animation of that. We're rewriting X into its decomposition. And this is sort of the key idea behind our snag check. We are using functors to cut through all of this noise of the algebra right here. We are untangling the braid into its pieces. The decomposition and the animation are just for the presentation's purposes. In the implementation of our algorithm, there's no requirement to compute all these braid rewrites. We just shove it all through the functors and run with it. So that marks the end of the category theory, and now I can wrap up this talk with 2 more slides about our main results. So in our paper, we've proved that our canonical form is computable in polynomial time. And this is super exciting because efficiently computable canonical forms are very powerful, and we also learned a little bit about what makes not equivalence difficult. Now, I should note that the worst case bound that we provide in our paper does not look friendly at all. Its highest degree is m to the 7th, where m is how many stitches there are in a program. Now, this is because our proof doesn't rule out the possibility that diagrams become larger every time we perform a step of our rewrites. We haven't noticed any such behavior in our limited testing so far, and we do have some suspicions that some clever mathematics might be able to alleviate those concerns. We also estimate that on typical machine knitting programs, the runtime will be quadratic in the number of stitches in the program. Nonetheless, we're extremely happy with our polynomial time result, and we've left more careful algorithmic analysis to future work. And then we've also formalized our canonicalization algorithm as an abstract rewriting system. We proved that it's sound and complete up to our 7 diagrammatic rewrites. It always terminates, and that it's confluent. With both termination and confluence, we have that the ARS is canonicalizing. And then because it respects our diagram rewrites and they're equivalent to those categorical axioms, we have a canonicalization of our semantics. That's all I have to share, and I'm very interested to hear your thoughts and questions.
Hello? Oh, great. Okay. Early on, you mentioned that you're interested in this partly to do optimization. And I assume to do optimization, you take the high-level program, and then you have a class of sort of low-level traces you can construct. And they're sort of all equivalent in one sense, but there's some other sense in which they differ, like, and you want to pick the one that's best in some sense.
Yes. So I've got a great answer for that. So it turns out these knitting machines are basically a vector-based architecture.
Yeah.
So they have hundreds of these needles, and they can all operate in parallel. So the way to make a program faster is to do as many stitches as you can at once. So we try to...
You're optimizing for speed?
Yes,
Okay.
optimizing for speed. There's also another couple metrics that we can optimize for, such as reliability and then geometric relation to the original, but we're mostly interested in speed right now.
Thanks.
So the main contribution of your work, I haven't actually read your paper, is of this abstract rewrite system. What, if any, role does it play in the word problem for group presentations? Is there some is there something that can be reused there, and do you use any existing algorithms for word presentations and for braid groups?
I mentioned the braid group earlier in this presentation, and then right here we have this step called braid, and that is exactly using the word problem for the braid group. So we're already using some of the group theory here, but here we're using category theory because these objects now don't have complete composition. So in terms of the word problem for groups, we're in a different setting, but we are in this sense solving maybe the word problem for twisted and volutive monoidal categories of a certain knitted structure. So there could be some applications, but we haven't formally looked into that yet.
Okay, maybe one more question. So it seems like the black boxes here, they don't know anything about the colors of what is coming in and out. So I guess that, would it be possible also to do some conditional knitting where you basically have some constraints that maybe if there's the same color you can do something, otherwise do something else? Or would that require some staging? Or?
So knitting machines don't have any way to take input or read like what their values of their colors are, so they just perform the same operations. So you could maybe perform some sort of actual traditional programming language, and then that operates based off of what's being knit and combine them. But currently we wouldn't be considering those equivalences. We're just considering with these static straight line programs for now.
All right. Well, let's thank Nathan again.